Tonight, we are going to talk about something that should not exist. A planet so enormous that it challenges everything we thought we understood about how planets work. A world so large that you could fit Jupiter inside it more than twice over and still have room left. And yet, this giant weighs so little that if you could somehow find an ocean big enough to hold it, it would float like a beach ball in a swimming pool. You have probably heard about giant planets before. Jupiter dominates our own solar system, massive and magnificent. But this distant world makes Jupiter look almost modest. If Jupiter were the size of a basketball, this planet would be larger than a yoga ball. And it sits over 1,200 light years away, orbiting a star in the constellation Hercules that you have never heard of. In a region of space we are only beginning to explore. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps. It is a small gesture for you, but it makes a tremendous difference for me. Now, into the story. To understand why this discovery matters so much, we need to start with some context. For most of human history, we knew only the planets of our own solar system: Mercury, Venus, Mars, Jupiter, Saturn. These were the wandering stars that ancient astronomers noticed moving against the fixed background. Later came Uranus and Neptune, and for a while, Pluto. But all of these worlds orbited our star. We had no idea if other stars even had planets. For centuries, astronomers assumed they probably did. The universe seemed too vast, too full of stars, for us to be unique. But assuming something exists and proving it exists are entirely different things. Finding planets around other stars turned out to be one of the hardest challenges in all of astronomy. Think about it this way. Imagine standing in New York City and someone asks you to spot a firefly hovering next to a lighthouse in Los Angeles. That is roughly the challenge astronomers faced. Stars are blindingly bright. Planets are tiny dots by comparison, producing no light of their own. They merely reflect starlight, and that reflected light is billions of times dimmer than the star itself. Then, in 1992, everything changed. Astronomers discovered the first confirmed exoplanets orbiting a pulsar, the spinning remnant of an exploded star. This was exciting, but pulsars are extreme objects. Finding planets around one did not tell us much about normal stars. The real breakthrough came in 1995. Astronomers Michel Mayor and Didier Queloz announced they had found a planet orbiting a sun-like star called 51 Pegasi. This planet was nothing like anything in our solar system. It was a gas giant, similar to Jupiter in mass, but it orbited incredibly close to its star. So close that it completed one orbit in just over 4 Earth days. So close that its surface temperature exceeded 2,000 degrees Fahrenheit. This shocked everyone. In our solar system, gas giants like Jupiter and Saturn orbit far from the sun, out where it is cold and ices could accumulate during formation. Finding one practically touching its star was like discovering a polar bear in the Sahara. It should not be there, and yet, there it was. This planet and others like it became known as hot Jupiters. They were the first type of exoplanet we found in large numbers, not because they are the most common planets in the universe, but because they are the easiest to detect. A massive planet orbiting close to its star creates observable effects. It makes the star wobble. It blocks more starlight when it passes in front. It leaves bigger fingerprints. And this brings us to the largest planet ever discovered, the world we are going to explore tonight, a planet called HAT P67b. The discovery came through something called the transit method. This technique works on a beautifully simple principle. When a planet passes between its star and Earth, it blocks a tiny fraction of the star's light. If you watch that star carefully, measuring its brightness over time, you will see a small dip as the planet crosses in front. The star dims slightly, then returns to normal brightness as the planet moves away. The amount of dimming tells you how big the planet is compared to the star. A bigger planet blocks more light. The timing of these dips tells you the planet's orbital period, how long it takes to circle its star once. This is where the HAT project comes in. HAT stands for Hungarian-made automated telescope, a network of small telescopes designed specifically to search for transiting planets. The project started in 2003 with a single telescope in Arizona. Over time, it expanded to include telescopes in Hawaii, Namibia, Chile, and Australia. This global network allows astronomers to watch stars almost continuously, catching transits that happen at any time of day or night. The telescopes themselves are not particularly large. Each one has a lens about 4 inches across, roughly the size of a good amateur telescope. But what they lack in size, they make up for in dedication and automation. These telescopes observe hundreds of thousands of stars every night, measuring their brightness with extreme precision, looking for the telltale dips that reveal transiting planets. Between 2005 and 2008, the HAT network collected observations of a star in the constellation Hercules, about 1,200 light-years from Earth. The telescopes noticed something remarkable. This star was dimming periodically. Every 4.81 Earth days, the star's brightness dropped by about 2.5%. That is a large dip. For comparison, when Jupiter transits across the face of our Sun, as seen from a distant star system, it would block only about 1% of the light. Something was passing in front of this distant star, and whatever it was enormous. After years of follow-up observations to confirm the discovery and rule out false positives, the planet was announced in 2017. And as astronomers analyzed the data, they realized they had found something extraordinary here. Here are the key facts about this world, stated clearly and precisely before we explore what they mean. This planet is roughly 2.14 times the diameter of Jupiter. If Jupiter measures about 88,000 miles across at its equator, this world stretches to nearly 190,000 miles from one side to the other. You could line up about 24 Earths across its diameter. By volume, you could fit roughly 12,000 Earths inside this single planet. It is the largest confirmed exoplanet ever discovered by radius. But here is where things become truly strange. Despite being more than twice Jupiter's size, this giant is only about 0.45 times Jupiter's mass, according to the most recent measurements published in 2025. Let that sink in. This planet is more than twice as big, but weighs less than half as much. That means its density is astonishingly low, only about 0.061 grams per cubic centimeter. For comparison, water has a density of 1 gram per cubic centimeter. This planet would float in water. It is less dense than cork, less dense than styrofoam, less dense than marshmallows. In fact, it is the second lowest density planet ever discovered. For the planet orbits an F-type star, which is hotter and more luminous than our Sun. This host star is about 1.6 times our Sun's mass and about 2.65 times its diameter. planet orbits incredibly close, at a distance of only about 6.1 million miles. It completes one full orbit in just 4.81 Earth days, racing around its star at tremendous speed. At that distance, the planet is being absolutely cooked. The equilibrium temperature is approximately 1800 Kelvin. That translates to about 2,800 degrees Fahrenheit, or roughly 1,500 degrees Celsius. That is hot enough to melt most metals. Hot enough that the planet glows with its own thermal radiation. This world is being roasted by its star every moment of its existence. So how can a planet be so enormous, yet weigh so little? This is one of the most fascinating questions this discovery raises. Jupiter, the giant of our solar system, is mostly hydrogen and helium, the two lightest elements in the universe. Deeper inside Jupiter, the pressure becomes so intense that hydrogen behaves in strange ways. Near the center, hydrogen is crushed so tightly it becomes metallic, conducting electricity like metal despite being made of the lightest atoms. This distant giant is also made mostly of hydrogen and helium. But unlike Jupiter, it is not compressed into a dense ball. Instead, it is puffed up like a marshmallow, heated in a microwave. The same amount of material is spread over a much larger volume, resulting in that incredibly low density. The intense heating from the nearby star is the primary cause of this inflation. When you heat gas, it expands. This is basic physics. The molecules in a gas move faster when you add energy, and they spread out to occupy more space. On Earth, this is why hot air balloons rise. The air inside the balloon is heated. It expands, becomes less dense, and floats upward through cooler, denser surrounding air. Now scale that effect up to a planet. The upper atmosphere is constantly bombarded by radiation from the nearby star. That energy heats the gas, making it expand. Over billions of years, this heating has caused the planet to inflate dramatically, but simple heating models do not fully explain the extreme puffiness we observe. Something else must be contributing. Scientists have proposed several additional mechanisms. One possibility involves tidal heating. If the planet's orbit is slightly elliptical rather than perfectly circular, the star's gravity would squeeze and stretch the planet as it moves closer and farther during each orbit. This tidal flexing generates heat through friction, similar to how bending a paperclip repeatedly makes it warm. Over billions of years, this could pump considerable energy into the planet's interior. Another possibility involves the planet's magnetic field. Gas giants often have strong magnetic fields, and these can interact with the stellar wind, the stream of charged particles constantly flowing from the star. This interaction could create electrical currents in the atmosphere. These currents could deposit energy deep inside the planet, heating it from within. A third explanation suggests that certain atmospheric layers might trap heat, preventing it from escaping efficiently. This could cause the interior to stay hotter than expected, keeping the planet inflated. The honest answer is that we do not fully understand why this planet is quite so puffy. It is one of the great unsolved puzzles in exoplanet science. This world, as one of the most extreme examples of an inflated planet, has become a valuable laboratory for studying this phenomenon. At such close distance to its star, the planet is almost certainly tidally locked. This means one side always faces the star, while the other side always faces away into the darkness of space. Our moon is tidally locked to Earth in the same way, which is why we always see the same face. This creates dramatic conditions. The dayside, the hemisphere facing the star, is constantly bombarded by radiation. Temperatures there reach nearly 3,000 degrees. The night side, facing away from the star, receives no direct starlight. It should be much cooler, though heat transported from the day side by winds prevents it from becoming truly cold. The boundary between day and night, called the terminator, would be a zone of constant twilight. Winds blowing from the scorching day side to the cooler night side would race across this boundary, possibly reaching speeds of thousands of miles per hour. The atmosphere is probably a violent, churning maelstrom, driven by extreme temperature differences. When we talk about this planet's atmosphere, we need to understand we are not talking about anything remotely like Earth's atmosphere. There is no breathable air. There is no oxygen. The atmosphere is dominated by hydrogen and helium, the same elements that make up most of the planet's bulk. But at temperatures approaching 3,000 degrees, exotic chemistry becomes possible. Many substances we think of as solids or liquids become gases. Titanium oxide and vanadium oxide, compounds used in paint and industrial processes on Earth, might exist as gases floating in the atmosphere, absorbing starlight and heating the upper layers even further. Some scientists think that the hottest layers might contain iron and magnesium vapor. Iron, one of the hardest common metals, reduced to gas and floating in the atmosphere. On the scorching day side, it might literally rain droplets of molten iron as the metal condenses in slightly cooler regions and falls. There might also be silicate clouds. On Earth, silicates are rocks: granite, sand, glass. These are all silicate materials, but at these temperatures, silicates could vaporize and then condense into clouds. Clouds of rock dust floating in a hydrogen-rich atmosphere, drifting on supersonic winds. The colors of this world are probably nothing like anything we see on Earth. Depending on what chemicals are present and how they absorb light, the planet could appear dark, almost black, absorbing most starlight. Or it could glow with strange colors, as hot gases emit their own light. Without being able to directly photograph the planet, we can only speculate based on our models. But here is something truly remarkable that recent observations have revealed. This planet is dying. It is actively losing its atmosphere to space right now, evaporating before our eyes. Multiple research teams have observed this planet using specialized instruments, and what they found is extraordinary. The planet has an enormous tail of escaping gas, extending more than 130 planetary radii ahead of it in its orbit. This tail is made primarily of helium, streaming away from the planet as its atmosphere bleeds into space. This is not a gentle process. The planet is losing approximately 20 billion grams of material every second. That is 20 trillion kilograms per second. To put that in perspective, that is like losing the mass of a small mountain every second. Why is this happening? The planet sits right at a critical threshold. Its density is so low that its gravity is relatively weak for its size. The escape velocity, the speed gas molecules need to reach to break free of the planet's gravity, is lower than for a denser world. Combined with the intense heating from the nearby star, which energizes atmospheric particles, and the result is catastrophic atmospheric loss. The escaping material forms a huge leading tail because of how the gas interacts with the stellar wind. As atmosphere streams away from the day side, it gets caught up in the flow of particles from the star, creating this enormous cloud that precedes the planet in its orbit. Think of it like a comet, but instead of ice and dust, it is a tail of hydrogen and helium torn from a disintegrating planet. Scientists estimate that at this rate of mass loss, the planet's atmosphere will be completely stripped away in less than 1 billion years. That might sound like a long time, but in cosmic terms, it is remarkably short. The planet has existed for over 1 billion years already. It survived that long because its host star was cooler and less active in the past. But now the star is evolving, becoming more luminous as it ages. This increased radiation is what triggered the runaway atmospheric escape we are observing, and the planet's fate gets even more dramatic. The star itself is evolving into a red giant. Over the next 150 to 500 million years, the star will swell enormously. When it does, it will likely engulf HAP 67b entirely. The planet that took millions of years to form, that orbited its star for billions of years, will be consumed by that same star, vaporized, destroyed, erased from existence. We are observing this planet during a very special moment in its history, a moment of crisis. It has survived for over 1 billion years, but now we are catching it in the act of dying. In astronomical terms, we are watching a slow-motion catastrophe. The planet is doomed, and there is nothing that can stop it. This raises a profound question. Why are planets like this so rare? If they can form, why do we not see more of them? The answer appears to be that we are seeing one of the last survivors. Planets with densities this low are inherently unstable when they orbit close to their stars. They inflate, their gravity weakens, and they begin losing atmosphere. This creates a positive feedback loop. As they lose mass, their gravity weakens further, which makes it even easier to lose more mass. It is runaway evaporation. Most planets that reach this state in the past have already been destroyed, their atmospheres stripped away, leaving only their rocky cores behind. Or perhaps nothing at all, if they were completely evaporated. HAT P67b survived longer than most because its star remained relatively stable. But now the star is evolving, increasing its energy output, and the planet's luck has run out. We are witnessing a process that shaped the architecture of planetary systems throughout the galaxy. Atmospheric stripping has carved boundaries in the distribution of planets. It helps explain why certain types of planets are common at certain distances, but absent at others. The universe has been running this experiment for billions of years, and we are finally learning to read the results. The distance to this world is almost impossible to truly grasp. The planet is about 1,200 light-years away. Light, traveling at 186,000 miles per second, takes 1,200 years to bridge that gap. When we look at this star tonight, we see it as it was 1,200 years ago. In the year 825, the Carolingian Empire dominated Europe. The Vikings were beginning their raids. Islam's golden age was flourishing. The light we see tonight has been traveling through space for that entire span of history. This means we are always looking into the past when we observe distant objects. The observations we make today show us the planet as it was over 1,000 years ago. If something dramatic happened to that planet yesterday, we would not know for another 1,200 years. The distances also mean we can never visit. Even traveling at the speed of light, which physics tells us is impossible for objects with mass, the journey would take 1,200 years. With our fastest spacecraft, it would take tens of millions of years. These distances create total isolation. We will never send a probe to this world. We will never collect samples. We will never take close-up photographs. Everything we know about this distant planet, we have learned by carefully analyzing the tiny amount of light that reaches us across 1,200 light-years of space. And yet, despite these incredible distances, we know quite a lot. We know the planet's size. We know its mass. We know its orbital period. We know its temperature. We know it is losing its atmosphere. We are beginning to understand its composition. From faint starlight alone, we can deduce the properties of a world no human will ever visit. You might wonder how astronomers can be confident about these measurements. After all, we are talking about a planet 1,200 light-years away. How can we know its size, mass, and density with any confidence? The answer lies in the rigorous methods of modern astronomy and the consistency of results from multiple independent techniques. The transit method, which revealed this planet's size, works on simple geometry. When the planet passes in front of its star, it blocks a certain percentage of light. The amount of blocking depends on the ratio of the planet's area to the star's area. Basic geometry. Nothing complicated. We know how big the star is from several independent measurements. Stellar models, which have been refined over more than a century of stellar physics, tell us how size, temperature, and brightness relate. Spectroscopic analysis reveals the star's temperature and composition. Distance measurements allow us to convert apparent brightness to actual luminosity. All of these measurements are consistent and point to a star about 2.65 times our Sun's diameter. Given the star's size and the amount of light blocked during transits, simple geometry tells us the planet's size. The calculation is straightforward. The planet is about 2.14 times Jupiter's diameter. This measurement is solid. The mass measurement comes from a different technique entirely. The radial velocity method measures how the star wobbles due to the planet's gravitational pull. As the planet orbits, it tugs on the star, causing the star to move in a small circle. This motion causes tiny shifts in the wavelengths of the star's light. These Doppler shifts reveal how fast the star is moving toward or away from us. The size of this wobble depends on the planet's mass and orbital distance. By measuring the wobble and knowing the orbital distance from transit timing, astronomers can calculate the mass. The latest measurements, published in 2025 using the NEID spectrograph, give a mass of 0.45 Jupiter masses with an uncertainty of about 33%. Both techniques give consistent results. The orbital period measured from transit timing matches the period from radial velocity. The mass and size are consistent with an extremely low-density gas giant. Everything fits together. Future observations will reveal much more. The James Webb Space Telescope can perform detailed spectroscopy of the atmosphere during transit. As the planet passes in front of its star, starlight filtering through the atmosphere will carry chemical fingerprints. Water vapor, carbon dioxide, methane, sodium, potassium, titanium oxide, vanadium oxide, all leave distinctive marks in the spectrum. By identifying these marks, scientists can inventory the atmospheric composition. They might also detect temperature variations at different altitudes, building a profile showing how hot the atmosphere is at different heights. This helps us understand energy flow through the planet. There is also the possibility of detecting weather patterns. If large-scale atmospheric features exist, Storms or bands like Jupiter's, they might cause small variations in the transit light curve. Detecting these would give us a glimpse of the planet's weather. The Hubble Space Telescope has already observed this planet multiple times, contributing to the detection of the escaping helium tail. Future observations will track how the mass loss rate changes over time. Is it accelerating as the star brightens? Are there variations driven by stellar activity? These observations will test our models of atmospheric escape. Ground-based telescopes contribute as well. High-resolution spectroscopy can detect Doppler shifts of atmospheric gases as the planet orbits. This reveals which molecules are present and measures wind speeds by detecting how fast gas moves toward or away from us. The science is far from finished. Every observation adds to understanding. Every measurement constrains models. This planet has been studied for nearly a decade since its announcement, and it will continue to be studied for decades to come. Stepping back to consider the broader context, before 1995, we knew of exactly 0 planets beyond our solar system. Today, just 3 decades later, we have confirmed over 5,700 exoplanets. Thousands more await confirmation. We have found planets of every conceivable type, from rocky worlds smaller than Earth to gas giants larger than Jupiter. From planets orbiting their stars in hours to planets taking centuries per orbit, we have found planets in habitable zones where liquid water might exist. Planets orbiting binary stars with 2 suns. Planets so close to stars that their surfaces are molten. Rogue planets wandering space without any star at all. The discovery of so many exoplanets has taught us that planetary systems are common. Almost every star you see in the night sky probably has at least one planet. Our galaxy contains somewhere between 100 billion and 400 billion stars. If most have planets, that means hundreds of billions of planets in our galaxy alone. And there are at least 2 trillion galaxies in the observable universe. The total number of planets is almost beyond comprehension. Somewhere among all those worlds, there might be life. This is one of the driving motivations behind exoplanet research. We want to find Earth-like planets with the right conditions for life as we know it. Hate P67. B is not such a place. It is a gas giant with no solid surface, temperatures that would destroy any known life, and an atmosphere dominated by hydrogen and exotic vapors. Life as we know it could not survive there. But studying planets like this helps us understand planetary systems as a whole. Hot Jupiters probably did not form where we find them. They likely formed in the outer regions of their systems and migrated inward. This migration can dramatically reshape a system, pushing smaller planets into new orbits or ejecting them entirely. Understanding how hot Jupiters form and migrate helps us understand which systems might be hospitable to life. This discovery is a piece of a much larger puzzle, a data point that helps us map the incredible diversity of planetary systems throughout the universe. What would it be like if you could somehow visit this world? The journey itself would be impossible with any technology we can imagine. At 1,200 light-years distance, traveling at the speed of our fastest spacecraft, the trip would take over 30 million years. That is longer than humans have existed as a species. But imagine you could somehow arrive there instantaneously. What would you find? Approaching the system, you would first notice the star itself. It is hotter and brighter than our sun, appearing intensely white with perhaps a bluish tinge. The radiation output is tremendous, flooding the planetary system with energy. As you drew closer to the giant world, you would begin to appreciate its scale. From a million miles out, it would appear as a distinct disk rather than a point of light. From 100,000 miles, it would fill much of your view, a curved surface stretching across your field of vision. The colors would be unlike anything in our solar system. Jupiter has distinctive bands of brown, tan, cream, and rusty red, created by different chemicals at different altitudes. This world might have similar banding, or it might appear more uniform, or display patterns we have never seen. If you could somehow descend into the atmosphere, conditions would become increasingly extreme. Near the cloud tops, temperatures are already severe. As you descended, pressure would increase. The atmosphere would become denser. Light from the star would fade into perpetual twilight, then darkness. There is no surface to land on. Gas giants have no distinct solid surface. As you descend, the atmosphere simply becomes progressively thicker and hotter. Eventually, pressure becomes so extreme that the distinction between gas and liquid breaks down. You would be immersed in a supercritical fluid, a phase of matter with properties between gas and liquid. Deeper still, if you could somehow survive crushing pressure and blistering heat, you might encounter stranger things. Whether this world has a metallic hydrogen layer like Jupiter is uncertain. Its extremely low density suggests any core must be small or diffuse. Understanding internal structure is one of the great challenges. We cannot see inside. We can only measure total mass, size, and behavior, then infer what might be happening in the deep interior from models. This giant planet is part of a broader lesson modern astronomy has taught us. The universe is far stranger and more varied than we imagined when we knew only our solar system. Every type of planet we thought we understood has turned out to have variations we never expected. The diversity is staggering. Every time we develop new instruments or techniques, we find things we did not expect. The universe continues to surprise us. This discovery is part of that ongoing surprise. The largest confirmed planet, a world so inflated that it would float in water despite being larger than any other planet we have found. An example of strange possibilities that emerge when physics operates under extreme conditions. I want to address something that often comes up when discussing discoveries like this. Some people ask, what is the point? Why spend time and resources studying a planet we can never visit? These are fair questions. First, there is the simple human drive to know. We are a curious species. We want to understand the world around us, including the universe beyond. This curiosity has driven every scientific advance in history. Knowledge has intrinsic value. Understanding the universe better is its own reward. Second, studying exoplanets teaches us about planetary physics in ways studying only our solar system cannot. We have one solar system to examine up close. We might think Jupiter represents what gas giants are like, but without other examples, we cannot know what aspects are universal and what are specific to Jupiter's history. Exoplanets give us broader context. By studying hundreds of gas giants across many systems, we learn which properties are common and which are rare. We discover phenomena like extreme inflation that do not occur in our system. We test theories against a much larger sample. This makes our understanding stronger and more complete. Third, the technologies developed for exoplanet research often have broader applications. Precision measurement techniques used to detect tiny brightness dips have applications in medical imaging, manufacturing, quality control, and other fields. Fourth, studying exoplanets is part of the larger quest to understand our place in the universe. Are we alone? Is Earth unique? Could life exist elsewhere? These are some of the deepest questions humans have ever asked. Exoplanet research brings us closer to answering them. There is also something to be said for inspiring the next generation. Young people today will grow up in a world where thousands of exoplanets are known, where astronomers can study atmospheres of distant worlds, where searching for life beyond Earth is an active scientific program. Some will become astronomers who make the next discoveries. Inspiring them is itself valuable. This planet is one of those wonders, a world that challenges our models, that stretches understanding of what is possible. Every child who learns about it learns that the universe is bigger and stranger than they realized. Every atom in your body was once part of a star. The carbon in your cells, the oxygen you breathe, the iron in your blood, all of it was forged in stellar cores billions of years ago. Those stars exploded, scattering atoms across space. Those atoms drifted for eons before coming together to form our solar system, our planet. And ultimately, you are made of star stuff. This is not poetry. It is literal truth. The elements heavier than hydrogen and helium that make up your body could only have been created in intense heat and pressure of stellar cores or explosions. And this giant planet we have discussed tonight is made of the same stuff. Its hydrogen atoms are identical to hydrogen in water. Its helium atoms are the same helium in balloons. At the most fundamental level, there is no difference between matter making up this distant world and matter making up you. We are connected to the cosmos, not just through observation and understanding, but through our very substance. We are part of the universe, not separate from it. When we study distant planets, we are studying the same materials and processes that gave rise to us. This is perhaps the deepest lesson of modern astronomy. We are not spectators watching a distant show. We are participants in a cosmic story that began with the Big Bang and continues today. The same physics governing distant gas giants governs cells in our bodies. The same gravity holding planets in orbit holds us to Earth's surface. Understanding this connection changes how you see the world. It makes the universe feel less alien, less separate. It reveals that everything is part of one vast, interconnected whole. So as you return to daily life, carry this with you. Remember that somewhere out there, over 1,200 light years away, a planet twice Jupiter's size is slowly dying as it orbits its star. It was there before humans existed and will be there after we are gone. It does not know or care about us, but we know about it. We care about it. And in that knowing and caring, we transcend our small place in the universe. If only for a moment, humanity stands at a unique moment in history. We are the first generation to know for certain that other worlds exist around other stars. The first to catalogue planets of other solar systems. The first to study atmospheres of worlds we will never visit. This knowledge changes how we see ourselves. We are not alone in a universe of barren stars. We are part of a cosmos teeming with worlds, many unlike anything in our experience, some potentially similar enough to harbour life. The universe is waiting. It has always been waiting, and now, at last, we are beginning to explore it. Thank you for joining me on this journey. If you found it valuable, please consider supporting the channel. Every like, every subscription, every share helps me continue making these deep explorations of the cosmos. Look up at the stars when you get a chance. Think about the planets that might orbit them. Wonder about what is out there. That wonder, that curiosity, that openness to the vast unknown. These are among the best qualities we possess. Good night, and may you never look at the stars the same way again.